Okay, we're going to do lesson 15.3 here. So real quick, this example, things we want to review: a discrete function. Remember, discrete functions are individual points. It is not continuous because they are not connected. In this particular case, this is a linear function because each x value increases by 10 for each ticket sold. You are getting 10 more dollars in cost. So this is just a quick review. Other things to point out: the function notation, t being number of tickets, the function f of t representing our cost. So to continue with this example, this is no longer a linear function. Instead, this represents an exponential function. And the way we can do that is by looking at how our y values increase. They are not at a constant rate. They're successively increasing by greater amounts, which if we plot the graph, we see if we connected this, would give us a curve going up, which is an exponential function. Now, this is still a discrete function because they are individual points. So to quickly answer our question in the table, again, f of t we said was a linear even though it was a discrete function. It just wasn't connected or continuous. G of n here is not a linear function. It is curved, but it is still discrete because they are individual points. So what are the limitations on the domains of these functions and why? Well, again, you can't buy a fraction of a ticket. Okay, you can't do partials. Therefore, they are whole values, in which case we get individual points, which makes it a discrete function. So some things I want to point out here as far as an exponential function. Look at the form, a times b to the x power. Exponential functions means our variable is our exponent itself. A cannot be 0. If a were equal to 0, then this whole value would be equal to 0. Therefore, it would just be a constant function. B must be greater than 0, and b cannot equal 1. If b is something less than 0, then we do not get an exponential function. We get something different, which we will look at later on. If b is equal to 1, then you're raising 1 to some power, which is always 1. So then, again, this becomes just a constant function. So as a review here, remember we said anything to the 0 power is 1, except for 0. You cannot do 0 to the 0. We said that's undefined. Also, anything to a negative exponent, we said to make positive, you do the reciprocal. Rewrite it as the reciprocal and use a positive exponent here. So now I'm going to fill out the table for this particular function, 3 times 1/2 to the x. So here's our a, our b, and then the x being our exponent makes it an exponential function. So I'm going to do the first value by plugging into the function itself and calculating the value. So I could do -1 as my exponent. Remember, if it's a negative exponent, we do the reciprocal. Now they've decided to do it as a fraction, but the reciprocal of 1/2 is 2, so it now becomes 2 to the first power. You simplify that, 3 times 2 is 6. So we now have f of x is equal to 6, so we have the point -1, 6. Now at this point, rather than calculate by hand, what I would recommend you do is go to y equals on your calculator, type in the function 3 times, parentheses, 1 divided by 2, close parentheses, raise 2, use the caret button, and then type in x. Then go to your table set, start at -1, make your delta table or triangle table go by 1s, since these all increase by 1s. Then go to your table, which is second graph, and then just look at the table of values to fill these in. I'll give you a second to do that on the calculator, and then you can check the values on the graph or on the table to see if they're correct. All right, so if you've done these on the calculator, you got 6 and 3 in your table. Then at this point, you got 1.5, which is 1 1/2. So the calculator is going to do everything in decimals. Now your book has done them as fractions, 1.5, 3/4, 3/8, 3/16. On your calculator, those corresponding values are 1.5, 0.75, 0.375, and 0.1875. Again, if you struggle with the decimals and you need those as fractions, go back to your main screen, type in 0.1875, do math, frac, and then it should give you 3/16. Okay, so if you've plotted these points on the graph, the first ones are pretty easy. Again, we had -1, +6, we had 0, 3. Then we had 1, 1.5, so things to pay attention to. Look at your scale. We're going by halves on here. So 1, 1.5, pretty easy. Then for point 2, we have 0.75. So we're halfway between a half and 1. Again, for myself personally, I would use decimals rather than the fractions like the book does, because to me it's a little bit easier to graph. So when you got the 0.3, 0.375, I know 0.375 is pretty close to 0.5, but it's a little bit below it. And then at the 0.4, we had 0.1875, which is just barely above 0. So again, here's another example of an exponential function. Here's my a, 3, my b is 4/3, and then my exponent is my variable. Again, they want you to do the first one by hand. Not exactly how I would do it, but we're plugging in -2 for our exponent. So right here we have -2, and we're wanting to simplify to find the value at -2. So we go in, since my exponent was a negative, I do the reciprocal, or in this case they're dividing, so I have 4 squared over 3 squared. Simplify that. So then I do, when you divide, there's the reciprocal portion of it, and I think that's just easier to do than do this step right here as a fraction. I would go immediately from here to here and do the reciprocal. But again, same thing in different ways. We simplify. 3 squared is 9, 4 squared is 16. We want to multiply those. Really, this is 3/1. So we multiply the top and we get 27/16. They want us to rewrite it as a mixed number. So 16 goes into 27 one time with a remainder of 11. And there's our value. Now, again, this is to get fractional values. And if you're asked to do so, then you might have to do this by hand. But again, I think the easiest thing is to go back to y equals, type your function in, go to your table, find the values in the table. Just remember, in the table they're going to do decimal values. So for this particular problem, I'm going to give you a chance again to go to the table. Instead of writing them as fractions, I'm going to put the decimal values that you should have gotten for this one. Okay, so the values you should have gotten here were 1.6875, 2.25, 3, 4, 5.3 repeating, and then 7.1 repeating. The book went ahead and did it as a fraction and did 7 1/9. So a difference in the two examples. The first example was an exponential that was decreasing from left to right, whereas in this one we see our y values are all increasing as we go from left to right on the graph. So just like we said, if you plot the points, you see this graph is increasing as we go from left to right, whereas in the previous example it was going down from left to right. So this is an increasing exponential function. So let's talk about why one is decreasing, one's increasing. So very simply, in the very first example, our b had a value of 1/2. That is something less than 1. So as our x's increase, our values decrease because this is a value less than 1. Think about it logically. If I put a negative exponent in here, I'm doing a reciprocal. Therefore, this is getting bigger. Whereas in the second example, my value of b was greater than 1. So again, if I did a negative exponent, I would do the reciprocal, which makes this smaller. But as I do positive exponents, this number gets larger. Therefore, it's an increasing function. So it's based on the values of your b here, whether it's increasing or decreasing. The a for both was 3, so that had no effect on the problem. So real quickly, let's address these two questions. What would happen to the function If a were 0, we talked about this. If a were 0, this whole thing is 0, so it's just a constant. If b were 1, then 1 raised to any power is always 1. So again, this becomes a constant function. Why is a geometric sequence a discrete exponential function? Because we're talking about individual points. Whenever we do a geometric sequence, we're talking about distinct values for x each time. So as we graph those, we get a discrete function. Okay, so we have an example 2 here that's given to you. Write an equation for the given function. It says when a piece of paper is folded in half, the total thickness doubles. That's an important term to note here. Suppose an unfolded piece of paper is 0.1 millimeter thick. The total thickness T of n of the paper is an exponential function of the number of folds n. So there's my exponent. The value of A is the original thickness of the paper before any folds are made. So if we go back, that was 0.1 millimeters. So there's your A. Because the thickness doubles with each fold, the value of B, or our constant ratio, what's happening to it each time, is a value of 2. So there's my B. And again, n being the number of folds is my exponent. So let's look at this example. A savings account with an initial balance of $1,000. Okay, again, that's what we started with. So if we go back to the previous problem, that was our A. So for our equation here that we're trying to write, that's my A value. Continue reading the problem. Earns 1% interest per month. Okay, that's what's happening to it. Now, 1% interest per month, that means the account balance grows by a factor of 1.01. You may be asking yourself, why is that the case? Remember, the $1,000 is always there. That's the 1. It earns 1% interest, which is 0.01 as a decimal. So every time per month, you're earning 1%. So you're taking the original, you're multiplying it by 1.01. 0.01 would just give me how much interest is earned. But 1.01 tells me the new balance based on the initial amount of $1,000 because I'm adding one whole $1,000 plus 1% interest of the 1,000. So make sure you understand that concept. Then time t is the number of months that it's in there. So again, our equation becomes 1,000 times 1.01, how much it's growing, our constant rate of change, to the t power in this case. Again, things to point out, function notation, the variable must be t. It was mentioned in the word problem as well. If you want to go back just to read the sentences here, your original balance again was $1,000, and the value of b is the factor by which it changes every month, which is 1.01. Okay, so here's an example where they give us 2 points for an exponential function, but we're trying to actually find the equation for the function that goes through those points. So the first thing we need to find is b, and it says by dividing the function value of the second pair by the function value of the first pair. Okay, what does that mean? The second pair is the second point because the x value increased. So we're taking 24 and dividing by 12. This being our first point, even though it's not the first point because it's a 1, it's the first point because 3 comes before 4. So if you divide 24 by 12, then you can't really see it here, but it is 2. Then it says evaluate the function for when x is 3, and you know that has to give you a value of 12. So you write the general form of the function. We are going to use 3 for x. We now have our b here is 2. And we're trying to figure out a. So we know the value of the function is 12. We're looking for a, b was 2, and x is 3. We simplify and work this problem out. We get a is 3/2. So a is 3/2, b is 2, and now we can put x back in, and now we have our exponential function. Something else to point out again, since b is 2, a positive value above 1, then this function would be an increasing function. Okay, so I want to do this problem with you. So the first thing again we want to do is find b. So we take 9/4 divided by 3. Again, 9/4 because it is the second point, because it occurs to the right, because 2 is greater than 1. So 9/4 divided by 3, if you need to work it out over here, 9/4 divided by 3, divide means multiply by the reciprocal. If I do that, I get 9/12. We want to simplify that, simplify any fraction. 3 will go into both, so 3 goes into 9 3 times, 3 goes into 12 4. So now I have the value of b. So the general form of the equation again is ab to the x. I can now substitute 3/4 in for b. I want to pick a point to use here. In this particular case, they've kind of led you to believe and use this one, and I would choose this one as well because anything with 1 in it is relatively easier to find. So here x is 1, and the value of the function would be 3. So 3 goes over here. Now it's just a matter of solving. So 3/4 to the first power is 3/4. To get rid of it, we multiply by the reciprocal. Again, this is not something I have to do, since y'all should know how to solve, but helping you out here. So those all cancel. The 3's cancel here, and I have a is 4. So now we have the general form, or the particular form of this function, which is a is 4 times b, which is 3/4 to the x power. And again, because our b here is value less than 1, then our function would be decreasing. So at this point, what I want you to do is I'm going to put the your turn problem here, and I want to give you a second to try to solve this, and then I'm going to put the answer up and you can check and see if you've done it correctly. So here's what you should have gotten. And I use function notation. F of x is equal to 10, so you should have gotten a was 10 times 5 for your b to the x. Again, since this is a value greater than 1, that would be an increasing function. So now for this particular lesson, you will be doing problem numbers 1 through 23 odd. 1 through 23 odd. I will also put the video up for 15.4 as well.